is on 2 years ago.
It doesn't have anything important.
All right. Yeah, I didn't say anything important. Don't worry about it. All right, 4 strokes. So we're talking about the 4 strokes. We got the intake stroke. So 1, the piston. See, you did what in your cut? Piston starts on what? Top dead center. Intake valve is opens, and it ends on
Right before.
bottom dead center. So remember, the stroke is always from the top to the bottom, always. It's this business about when the intake valve opens and closes is not quite accurate, but that's okay. It's mostly true.
Just.
What's the next stroke? Okay, it's interactive here, so help me out. I don't know what I'm doing.
Piston starts on BDC.
Okay, thank you. So, starts on
BDC.
bottom dead center, because now we're at the bottom.
Both valves closed.
Okay, both valves closed.
Ends on PDC.
Spark plug fires. And ends on. Very good. Top dead center. Thank you. Okay. What's after compression?
Ignition.
Power.
No, ignition is not a stroke. Power starts on
Top dead center.
top dead center. All right, you're getting it. 2, both valves
Closed.
closed. Ends on
Bottom dead center.
B, D, C.
You decided that was there.
BDC.
Bottom dead center. All right. The pressure in cylinder is the greatest just after top dead center. So starts at top dead center, then boom, pressure is the greatest right about there. Most of the gases are burned up just after top dead center, at about 14 degrees. So 14 degrees after top dead center. That's what the A is after. Yes?
What do you mean by gases? Do you mean the fuel?
Yep, the fuel. Well, it's going to be fuel air mixture.
Okay.
So that is the gases. The gaseous fuel, the gaseous air combined. What comes next?
Exhaust.
Exhaust. I know I go into this a little bit, but I guess maybe now I could back up just a little bit and talk about this whole power thing. And we have to think about what's really happening in this power stroke. Is that the fuel air mixture obviously is ignited. In reality, it's ignited it's not ignited in the power stroke at all. It's ignited in the compression stroke, but we'll get to that. And so it ignites and the piston's still really coming up and it compresses everything. It starts this flame front of burning. And so what happens is it's not an explosion by any means. If it is an explosion, something bad has happened and you are going to damage the engine and could have a catastrophic failure. So it's an actual burning of expanding gases in a pressure wave that is going to push on the piston. Much like if I had to move this table over to there, I would want to come over here and do a pressure against it and start moving it. I would not want to take a sledgehammer and do it hit by hit, which is what happens if the fuel explodes. It's hitting it like it's hitting the piston with a huge hammer. Whack, and then make it go around, rather than taking the piston and giving it a nice good push. So that's very bad. So these expanding gases are pretty much, you have to figure they're going to start expanding, but at the same time the piston is already now working its way down, and the gases are expanding and pushing and pushing. So that's why the greatest pressure is really just after top dead center. The piston is just starting to come back down, and the gases have really expanded, giving their hardest push right about that point. And then it's going to lessen off as the piston starts going down. So exhaust starts on.
Bottom dead center.
Starts on. Very good. Starts on bottom dead center. Exhaust, I just abbreviate EX as exhaust valve is open and ends on
Top dead center.
what comes next? Intake. So we just keep doing it over and over and over again. All right. Let's talk about efficiency. Well, that's the basic four-stroke principle right there. The basic simplified version. I'm going to bring it back around. I know I will. Yep. And we're going to talk about what's more realistic. Yes.
Are most aircraft engines going to be non-interference or interference where the valves will occupy the same space?
That's where I'm going with this. And an interesting point. The stuff that I have talk about them being, don't use the interference, it's called overlap. But I'll prove something to you that Lycoming doesn't do that, which is very strange. So, but definitely Continental does. Lycoming not so much. So efficiency. All right. So this is a what kind of engine?
Lycoming 0290.
Well, that is not incorrect. It is a heat engine, right?
Yeah.
So we're going to talk about thermal efficiency. And as we talk about odd stuff like this, you might think, well, wait a minute, I want to be an aircraft mechanic. I don't want to be an aircraft engineer. I'm not going to develop engines. I mean, why do I care about thermal efficiency? Well, in understanding thermal efficiency, you understand what's happening with an aircraft engine. When you understand exactly what's happening with it, you can diagnose its problems and fix what's happening. If you just have this basic, well, I know the piston is bolted on this way, and that's how you bolt it on, you lose this overarching knowledge of what's wrong with them. Because, let's be honest, it's rather simple once you've been trained to disassemble, clean, inspect, and reassemble an engine. In fact, you can even, if you did the same engine over and over again, now you just become an assembly line, and you can pretty much hire a robot to do that, or build a robot to do that. You don't have to hire them, you don't have to pay them. But where you really start making your money, and it's funny, I always think this, and I actually read it this past week, or somebody said it in one of the seminars, like where you make your money is when you can troubleshoot something. When somebody says, this is what it's doing, and you go, I understand it, I know why it's doing that, and I can fix that, right? And you'd be just surprised how many simple things I've even seen in my career about, people chasing stuff off on one direction, and it's like, I've been to 6 different mechanics and they still haven't been able to diagnose this. Just simple examples. I've had people come in and it's like, because I was an engine overhauler shop, they're just at their wits' end. It's like, I think I might need an overhaul. Well, how come? Because my engine just runs so stinking hot. It's always hot all the time. I can barely climb out. I got to climb a little bit, then I got to level off and go straight forever. You get the temperatures to come down, then I can climb a little bit, straight forever. Okay, well, let me ask you, have you, what about your oil cooler? First mechanic overhauled the oil cooler. Oh, what about the vernifuller valve? That's the thing that controls the oil that goes in the cooler. It's brand new, we've changed it 3 times. Okay, how about, well, sometimes baffles, had the baffle seals changed. 2 different mechanics worked on it. They are absolutely perfect, as tight as can be. We've done, well, why don't you bring it in and let me take a look at it? First thing I do is take out the oil temperature probe and calibrate it. I'm like, well, your engine's not running too hot. It's actually running too cold. Your gauge was lying to you the entire time. It's just like little things you start thinking about, understanding it. Or, go back to somebody who's burning up exhaust valves. And you're like, okay, why are you burning up an exhaust valve? And you can actually get into how an exhaust valve is cooled inside the engine. What makes it cool? What makes it hot? How do you solve those problems? So that's why we talk about this stuff. So I already said this, but if I don't write it, my notes will be all off. So a recip, which stands for? A recip engine is a what kind of engine? Heat engine. And this is repeating itself. So heat produced by burning fuel in the cylinders causes expanding gases that does work. That does work. All right, I gotta change the page here, so I gotta wait for Michael to catch up over here. All right. Got it. Cool. You have to be as fast as him. Slower than him, you're gonna lose out.
Slower, no, I think Oscar's slower.
Right, heat. If I went too fast, she's got to say something. Heat work can be expressed as how do we express heat?
Kelvin?
Fahrenheit.
That's a measurement of.
Celsius.
It's a measurement of. You know this. Just leading you down the wrong thing.
BTUs.
What's the BTU?
God dang it.
What is the BTU? British
British thermal unit.
thermal unit. British thermal unit. All right, for the new people, the old people. When I say for the new people, it means that you guys already heard this a million times, so you can just tune out. So for the new people, I used to be a mechanic examiner. So at the end of this 2-year program, you are going to be eligible to go out and take your exams, which consists of, it's the interactive part,
Oh.
three written tests and your oral practical. So 3 written tests, oral practical. I did the oral practical part. So I know the questions that were asked. And I will also tell you that the day you graduate here, you are well prepared to go take your exams. How did all your classmates do?
Justin passed with flying colors.
Of course.
He said it was super easy, and that I have nothing to worry about.
Yeah. And I think if you asked all of our graduates, they would all say the same thing. And I telling you right now, I'll say it again and again, you should view the oral practical. If you went to this program, you should view the oral practical as a day to celebrate and to show off your knowledge. You have absolutely nothing to fear. I'm telling you, when I was an examiner, this is a long time ago. I didn't even teach here. I mean, I taught here adjunct, but very part-time at that point. I knew that when I had a Sac City person coming to me, it was going to be an easy day. If they got a question wrong, I was shocked. If they couldn't do a project, I was shocked. I mean, it was like, wait a minute, what's happened here? And it was usually one of those people who probably shouldn't have made it through. Relied on everybody else to do their projects for them or something. But just I didn't mean to offend you. But yeah. I am, so straighten up. Was I right? So no, I want to tell you that, if that's something that's like looming, it shouldn't. You should just put it out of your mind and go, "Pff, you got it. There, I'll look around this room. I don't know some of you, but the guys and gals that have been with me for a whole semester now, there's not a one of you. I mean, look, Duncan back there. There's not a one of you that isn't just going to blow through this thing and just go. Psh. So don't even think about it. You got it.
I knew you would say my name. Someone would say my name or something.
Duncan's hiding back there, so I gotta wake him up a little bit.
Duncan, get
He's
forward.
been too quiet. He's been too quiet. I gotta move him up front. So.
His legs popped up and everything.
He's too cool for school. All right. Anyway, I guess I tell you all to tell you that I know for a fact that what is a British thermal unit is an oral question. A British thermal, and they actually want you to know this. So what is a BTU? British thermal. Well, what is it though? Can't you say, oh, it's a British thermal? It's a British thermal unit. Next question, please. Now, what is it?
Mic drop.
Yes. It is equals or is the heat required to raise one pound of water 1 degree F, because I know you're going to ask 1 degree because it is the British. And notice we won't even take claim. Hey, that's the British, so don't even ask us. It,
Liters or like
the whole system of, that's why my
No, not
joke,
currency though.
the whole system of the foot and the inch, it was all the king's stuff.
I'm
Leave him alone.
That's the joke I always say. My grandparents didn't fight in World War II, so we could do the. It has nothing to do with that. You guys ever picked up on that?
Oh, God.
Oscar.
It's also 778 foot-pounds of work.
Right? They don't use inches over there.
They gave up on their own stuff, I think. They used.
Yes, they did.
Although I don't know, my knowledge of the British pretty much envelops Top Gear and Grand Tour.
Old
So
Top Gear,
yeah,
not new Top Gear.
yeah, old.
Old Top
Jeremy Clarkson stuff. Okay,
778 feet.
foot-pounds of work.
It looked like.
FTLB of work, foot-pounds of work. Yes. All right, but you do need to memorize that. Now, with the whole story about me being a DME and you guys doing great, was to remind you that the BTU is the amount of heat required to raise 1 pound of water 1 degree Fahrenheit, because you got to know that. And then you don't ever have to know that again, because I could probably find you the greatest aircraft mechanic in the world. And I'd say, define British thermal unit. And he goes, I don't know, but I can fix this. Okay, so one, this is, do I have to write it out? POU, 1 pound. 1 pound of petroleum, that's gas. 1 pound of petroleum, and by the way, 6 pounds. It's 6 pounds per gallon of avgas. So 1 pound equals 1/6 of a gallon. Follow that?
What? 1 pound? Oh,
1 pound of fuel.
1 pound of fuel is equal to 1/6 gallon.
Yep. How many pounds does a gallon of avgas weigh?
6 pounds.
6 pounds. You need to know that. Gallon of avgas weighs
6 pounds.
6 pounds. So 1 pound of petroleum is 1/6 of a gallon. And the point here is I didn't convert it. I just found something that said 1 pound of petroleum. I'm copying them, but I had to stop and go, well, how much is that? Well, that's about 1/6 of a gallon. 1/6 of a gallon can produce about 20,000 BTU, or 15,560,000 foot-pounds of work. So, what the hell's wrong with us then? How many foot-pounds of work are you getting out of your car for 1 pound, 1/6 of a gallon?
Not that much.
Not that much?
I'm going from the end of the street with one.
Why not? Heat loss, thermal inefficiency. Thermal inefficiency. Let's talk about thermal efficiency. I think thermal inefficiency is a better term, but I wrote thermal efficiency here. Is the percent of work an engine gets for that pound of fuel. Of work an engine gets for that pound of fuel. Pound of fuel. So, all right, so what happens to all this gas? Well, about 20 to 30% is used for power. That's not very good.
That's saying horsepower alone.
Yep, about 15 to 20% is lost in heat radiated from cylinders. We've got another 5 to 10% is friction loss. Now, it seems to me like that whole friction loss should be up here in the power, because really the fuel produced the power that pushed the piston, but then you have friction loss inside of the engine, which I think I don't want to make it too difficult. Just a thought there. Which means that 40 to 45% is lost. Oops, lost. I put an S in there. Lost. Out of the exhaust. So that's not very efficient now, is it? Let me see. Sometimes I have stuff on here I shouldn't do. Yeah, I'll just tell you what I'm not going to tell you. So my next notes, I had thermal efficiency can be computed as follows. Indicated thermal efficiency equals indicated horsepower, which is IHP, divided by 33,000, because that's a constant, divided by weight of fuel burned, divided by the heat value times 778. Anyway, I go on to show that a 85 horsepower engine, with a whole bunch of math, has a thermal efficiency of about 23%. So bottom line is, heat engines, piston engines, recip engines are about how efficient?
20 to 30%.
20 to 30%.
That's pretty crappy.
That is quite crappy. What are you going to do about it?
Make it better.
Turbo.
We fix them. We can't really do much about it. So if we think about that, it's just kind of,
Job security.
it's job security. Yeah. Speaking of fuel, we're having some big fuel problems with aviation. You guys following that?
Ridiculously expensive now.
We're going to talk. Well, no, actually, I just filled up my airplane for less than I filled my car up. I mean, not dollars wise, but price per gallon.
Really?
I went to Calaveras. It was only like $4.60 a gallon or something.
No, that's not
Yeah.
bad.
That was still $250.
But still.
No, so we'll talk more about this in the next class, 312, 313, about the composition of fuel. But so you know that we use a fuel in aviation called 100 low lead. Now, you hear the name 100 low lead and you think, Well, that's nice. It's 100 octane that has low lead. It's only called low lead in comparison to the extreme lead fuel that they used to have. Hyper extreme lead. So our 100 low lead is got, I forget what it is, something like 4 times the amount of lead that was ever put into the most leaded car gas ever used. So it is a tremendous amount of lead, and it creates problems not only for the environment, but if you don't care about that, it actually creates problems for the aircraft engine itself. In hearing about where we're going with this unleaded, they're trying to do unleaded fuel, and where they're going with it, they're anticipating a lot fewer problems with engines. And I just, in reading what I'm reading, I'm almost, between the lines, I can almost hear this like extension of maybe a TBO. I don't know. Because they're saying, the lead, it gets into the oil, and then it's a contaminant, and it fouls spark plugs. And there's so much talk about how leaning is better because it reduces the lead burning in the fuel and all kinds of stuff. But anyway, so when I was at Lycoming School many years ago, one of the guys in the class was a fuel engineer from Shell. And he talked about the fact that, that was his job. He was there to learn about an aircraft engine because he'd never seen one in his life, but he's working on the new unleaded fuel. Like I said, this was 3, 4, 5 years ago. And they had a Lycoming 540 that they ran and they tested the fuel with. And he had to do some maintenance on this engine, so they sent him to Lycoming School so he could at least see an engine and kind of understand a little about Lycoming so he could do this. And so, one of the guys asked him, where are we with this fuel? And he said, you don't really think about, as just a normal person, what it entails. He goes, but if you think about it, not only do we have to create this fuel, see, our engines need high octane. Otherwise, they detonate. And that detonation, like I said, is like hitting a piston with a sledgehammer. And it can destroy an engine in less than 1 minute. I mean, catastrophic disassembly, failure, falling out of the sky type damage in less than a minute. So we need this high octane because we're running higher compression engines, so to speak. Actually, not compared to cars, but enough that we need the high octane. And so we have to have this high octane. And so the only way they can get it is by adding all of this lead to it. And so he said, if we create this fuel that has the high octane without the lead, he goes, not only does it have to maintain this high octane rating consistently, but it has to maintain that when mixed with any other possible fuel ever produced could be out there. So if somebody mixes it with something, if you mix the 100 low lead with this, what is the chemical reaction? It still has to maintain 100 octane. If you put 91 octane car gas in it and this stuff, you got to have that still the average in it. So he said it was quite a nightmare. But anyway, GAMI has produced it. I think GAMI. And so, yeah, they heard down in the Bay Area, of course, oh, there's unleaded fuel. They stopped selling it at like 100 octane at Palo Alto. So you can't even, anyway, yeah.
Altitude also be a factor in the fuel?
Not really. Oh, yeah, it has to perform at altitude. Yeah, the volatility and stuff, absolutely, without a doubt. Yeah, you got to maintain that.
Why is it so strict on like it has to be air? It has to run on the same kind of fuel that's ever been out there. Like you wouldn't put gasoline in a car that's tuned for ethanol or something like that.
Well, you just have to. People do weird things in aircraft, and then if somebody dies, then they go back to Shell and then they sue them. So there's an airworthiness directive out there that did me quite well in my day. And there was an air show here in Sacramento somewhere. I forget where it was exactly. But the Chevron accidentally got a little bit of Jet A into the 100 low lead line. Just a little bit. And they found out about it. And so they produced, and so you have to put in your N number when you get fuel. It's registered for this reason. And so what they had to do is go back and they had to look at all of the N numbers that truck filled, and they called them up and said, hi, we're from Chevron, you get a new engine. And I did a lot of antique engines that, you just couldn't go to the factory. I did, I don't know, probably at least a dozen engines, I think, off that AD. So yeah, Chevron bought everybody new engines.
Wow.
Yeah.
Textron, I guess, sent out something for the 150s to 180 models. They're allowed to use biofuel, I guess, now?
It's very specific
Yeah.
to models. Yeah.
I kind of saw it pop up on my feed once.
Yeah, like it will not apply to my airplane, and a lot of the new unleaded fuels will not apply to mine. So, okay, back to this. Let's see. So not credible. Okay, so number one, volumetric or heat efficiency, not so much. All right, what are we gonna do about it? I got nothing. I'm done. So, all right, now we got to talk about volumetric efficiency. And this is where a lot of attention is focused in cars, aircraft, everything. How do we increase this volumetric efficiency? So volumetric efficiency is really, what it's saying is, that we've got this piston that's, did what in your cup? That's going up and down in here, right? And so here's where my exhaust port is, and here's my intake port. So what's causing the fuel and air to go into the cylinder to begin with? Well, it's kind of like a plunger. This thing pulls back. It's got rings in there. It's like a syringe. You guys know that, you bunch of junkies. So you got the syringe. Yeah, see? I know my audience. So,
Yeah, go in between your fingers.
so the piston comes back and it creates a low pressure in here, if you will, and it draws in the fuel air. Well, that's all fine and well if you're using a syringe. You know, if I had a syringe and I put it in a cup of water and I pulled it back, it's going to fill up 100%, right? 100% volumetric efficiency with that syringe. But this thing's moving up and down at a rate of, 2,000 revolutions per minute. So that piston's moving really fast. So, by the time the piston's coming down, the air says, oh, we're supposed to go in. The air starts to go in. The piston's already turned around. It's pushed. Oh, now it's time to go the other way. Okay. So it's not filling up the cylinder by any stretch of the imagination. It's only partially filling the cylinder. So if you're only partially filling the cylinder, this is off an O200. So there's 4 cylinders on O200. So this would be 50 cubic inches, roughly, right? So, did I do that right?
Say that again?
Yeah.
So an O200,
Uh-huh.
there's 4 cylinders on an O200.
50.
So if about 50,
Somewhere around.
50 cubic inches per, it's actually C85, but I can't do that math. So O200. So 50 cubic inches, and if the volumetric efficiency, it's pulling back and it's turned around, the valve's closing and it's starting to go, and it only got half the air in there, now it's how many cubic inches?
Less.
It's like 20, only got half, it's only 25 cubic inches. So how do I get it up to 50? Well, I make a cylinder twice as big, right?
Duh.
Forced induction.
Turbo.
I never got there yet.
Oh,
Okay,
You're too smart.
I know. Right, do you follow me on that? The volumetric efficiency. If this is 50 cubic inches, and when you measure cubic inches, what that really is, they use a liquid, and they take the piston, and they put it all the way at bottom dead center, and fill it up full of liquid, and then put the cylinder on top dead center, and how much it pushed out is the displacement of the cylinder. That's where they get that. That's the 50 cubic inches. So they would measure that water, go, oh, look, we just spit out 50 cubic inches. Everybody follow that?
Yeah.
And then multiply it times how many cylinders are there. Go, well, look, we spit out 50 and there's 4 cylinders, then it's
Roughly 200.
200 cubic inch engine.
Crazy.
All right, that's how it works. So, but that's static. That's doing it in a laboratory. That's pulling the piston all the way down and then stopping it and filling it full of water and then pushing. All right, but it's sitting there running really fast. And so, follow. I'll make sure everybody got that. Okay, it's going down. The valve opened. It sucked it down. Valve closed. Moved back up. But it happened like 800 times faster than I just said it. Not quite that much, but follow. So, 50 cubic inches of air never found its way in there. The piston turned around and went the other way, so the air didn't flow that well into it. So that's called volumetric efficiency. How much did we get in there? Now it's a 50 cubic inch cylinder. I want 50 cubic inches in there. But if volumetric efficiency is at 50%, how much did I get in there? Only 25 cubic inches. So suddenly my 200 cubic inch engine just dropped down to 100. And so, yeah, then the horsepower goes. Now, if we could turn it around and figure out how to get 50 in there, my power is going to go way up. Okay? So that's what we got to work on. So volumetric efficiency, valve overlap, and ignition timing is what we're going to talk about. So valve overlap and ignition timing. Your valve timing is not going to have anything to do with volumetric efficiency, really, but for some reason I put it all on the same line, so we'll just keep it that. So now you know what volumetric efficiency is, so I can say volumetric efficiency in a normally aspirated. All right, Mr. Lawson, your wife's a nurse?
Oh, shit.
Yeah, what does aspirated mean?
She's a nurse.
Didn't I say she's a nurse? I said your wife?
I know, but then you asked me what the A pirate was,
Aspirated.
as pirates.
As pirated.
No, it's like,
What is as pirated?
It's like breathing. Like you're lack of breathing. Like if someone's aspirating, they're not breathing.
Oh, anybody know what aspirating means? If you aspirate?
Doesn't that mean there's air where there's not supposed to be air?
Go ahead, Duncan. He's nodding.
Yeah, you get fluid water in your truck.
He said it very nicely. It means you basically inhaled your own sick. That's what alcoholics and drug addicts sometimes die of. They vomit and then you gives into your. So how does that relate to engines? It doesn't. So don't. So why did I tell you that? Just to give you a nice visual. I don't know. Okay, volumetric efficiency of a normally aspirated engine is always less than 100%. Unless it's not running. Okay. So what I made up. Okay, what does normally aspirated mean? Well,
Naturally?
it means that, naturally, it does not have a turbocharger, supercharger, something pushing the air in.
No forced induction.
No forced induction. So, most of your cars are now turbocharged. So you have a turbocharger, which is an air compressor that is pushing air in. So the minute that valve opens, rather than depending on the piston to suck the air in, you got something blowing it in. So it's like one of those sleep apnea things, I think, right? I see the commercial. I don't have one, but yeah, you open your mouth a little bit. Right? Okay. Or scuba diver. That's. Well, you push the button on the front. Do I have any scuba divers?
Yes.
Yes. Okay, so you know what I mean. Am I wrong?
Yeah. No.
Not entirely.
You walk into something, you swim along something, you push a button in, it's gonna force induction, is it not?
Yeah.
Okay. I killed them. All right, so normally aspirated means that the piston is sucking and drawing the air in of itself. So if it's not normally aspirated, then it's either called forced induction, is what I would call it. So, all right. So it's always less than 100%. Let me see. I have to write volumetric efficiency over and over again. Volumetric efficiency, there we go, VE, I just made it up, is greater at wide open throttle. Wide open throttle. Which, by the way, is actually WOT. That is an actual
What?
wide open throttle. That is an actual acronym we would use in aviation. Okay, so why would my volumetric efficiency be better at wide open throttle?
Because you're letting in the most fuel.
You're letting in everything. Most air, most fuel, most everything.
Everything is open all the way.
Yeah, pretty much. I mean, you got it. So we have a pipe basically that's going into the intake system, and we have a carburetor, fuel injector, something else. But inside there, we've got that butterfly valve that opens and closes. Well, if it's mostly closed, then this thing is really sucking hard. It's like trying to suck a.
Suck the golf ball through the garden.
No, I was going to go with a shake, a milkshake. Like, you're trying to. But it really isn't a good analogy because there's no throttle on a milkshake. But it's pulling hard and it's not coming through that restriction. And then when the restriction is gone, of course you just lose the restriction. That's all. Because the throttle is a restriction, and that's why we have a high vacuum in the intake manifold. So the pipe that attaches to this is called an intake pipe or intake manifold. And if I were to measure the pressure in there, so the carburetor is over here with the throttle valve, if I had to measure right here at an idle, this is pulling really hard and it's really not getting much in there. So it's a huge vacuum, big, big, big vacuum. And then when I open up the throttle, the vacuum starts to go away. Now in cars, we think of it more that way. Big vacuum, not so much vacuum. In aircraft, we think about it in opposite terms. We think about it in more of a pressure, and that is at wide open throttle, we are very near atmospheric pressure, or 30 inches. At closed throttle, we are at a much lower pressure, 14 inches, 12 inches. That's inches of mercury, by the way. So, all right, so the opposite is true then, less at idle. I just explained why. What else ruins volumetric efficiency? Sharp bends do. Sharp bends in intake. Sharp bends in intake. Reduce efficiency. Reduce efficiency, and higher temps do too. Higher intake air temps.
The colder the air, the denser it is.
Yep. The colder the air, the denser it is. The denser the air means more air. More air means higher volumetric efficiency. So higher intake air temps reduce efficiency. So you have somebody, and you take a look at their airplane, and you can just kind of evaluate what they've got, and you might be able to see, I'm going to get you a little bit more horsepower. How am I get you more horsepower? Well, if it's a production aircraft, a legacy aircraft, Cessna, Piper, you're not going to do anything because it's the way it's made. You're not supposed to mess with it. But it's a home built. Well, you got some sharp bends there in your intake manifold. We can reduce that. You've got your air intake runs right. Why you run it around your exhaust manifold before you go up in? We can get rid of that. And just wire the throttle wide open, and that'll certainly help. All right, to increase volumetric efficiency, valves open and close at times other than BDC and TDC. So to increase efficiency, volumetric efficiency, valves, that's your intake and exhaust valves, open and close, close at times other than BDC and TDC, like the animation showed you. It was always at bottom dead center, at top dead center. Okay, that's not necessarily how it works. So what I'm going to do is I'm going to run you through how your book shows it, and then we'll dissect something after that, which you guys will be able to understand even better. So a couple of terms. So valve, valve lag, that equals opening or closing after TDC or BDC. So like if I said the exhaust valve has got a 2 degree lag on closing, that would mean that it's going to close 2 degrees after when it should have. Valve lead, just the opposite. Or maybe that's valve lead, I don't know. Valve lead, opening or closing. Closing before TDC or BDC. duration. Duration is time valve is off the seat. That's going to be a very important point for us. Time valve is off its seat. In other words, open. If it's off the seat, it is open. All right, let's go through this. Let's see. I don't like how I wrote this, but I'll just stick with it because it'll make sense. Intake valve. And this is going to be valve timing is from 83, your 8310, so I'll just say the FAA book. And I think I have a picture of it. Not 4313, 8310. 8310? I do not. It is. Oh, there it is. There. 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 Finally. All right. We'll just edit that part out. Nobody will notice. All right. This is right out of your book. Valve timing chart. And I think this is horribly confusing. So we got to start. You have the intake stroke here, and the start cycle 50 degrees before top tech center valve opens. Here's your ignition over here. Here's your compression stroke. Here's your intake stroke. It's the valve is opened through here. And so what I'm going to do is explain this in a way that a normal person can understand, because that was just horrifically bad. All right, but that's what I'm talking about right there. So intake valve. So here are some things about it. So let me see. This is a good place to stop, actually, because it's going to get into it, and I don't have to start again tomorrow. So we'll just stop right here. Now,